All right, so now let's go ahead and take a look at another problem where we're estimating the area underneath the curve of f of x equals to x squared minus 1 on the closed interval from -2 to 1 using three rectangles and midpoints as sample points. Now, as usual, the first thing to do is to figure out what will be the width of rectangles, or in other words, what is going to be the width of our subintervals. So we'll get here, delta x is going to be equals to b minus a, which in this case is 1, minus a -2, over the number of subintervals. In this case, our n was equals to 3. So what does that give us? We're going to get 1 minus a -2, which is a 3, divided by 3, which is going to give us a 1. Perfect. So now we know the width for our rectangles, and I'm going to go ahead and mark the subintervals here. So we're going to start at the -2, then we're going to go all the way to a -1, which is right over here, then to a 0, and then to a positive 1. Perfect. And this ones here are our delta x. Okay, now let's go ahead and get our sample points. Now for this problem though, I am going to do something different here. I'm going to go ahead and label my sample points here as xi. Alright, now because we are focusing on midpoints here, our sample points are going to be in between here. Now the first one, I guess this one's a little bit easier than the previous ones, that we can easily see it, but well, let's actually calculate it, because I'm going to do it a slightly different way than the one I did the previous problem. And this way, I would consider it kind of like a shortcut. All right, so for the first midpoint, we take a look here at our subinterval. We went from -2 to a -1. All right, so on the interval from -2 to -1, what is the midpoint? Well, we use the same formula. We go ahead and take a look at the endpoints, -2 plus -1. There we go. We took a look at the endpoints, added them up, and then divided them here by 2, which in this case is going to give us -2 minus 1, that's a -3, divided by 2 is going to give us a -1.5. And this is what I'm going to call here my first sample point, x1. All right, so we're going to have here the x1 right here. Then what about the other sample points? Now, it is true, we could go ahead and find the midpoint between -1 and 0 using the formula that we just did, but here's a shortcut. Now, notice here that since we're using midpoints, once you have the first one, and since we're talking about subintervals that are equally spaced, or they all have a width of 1, well, you can actually get the next sample point by adding a delta x to your first midpoint. So in other words, to go from, and I guess I'll write it here, x1 was equals to a -1.5. To get the next sample point, what we can do here is add the delta x, which in this case was 1. So if I take the -1.5 and add 1, where do I land? Well, I land at the next sample point, x2, which in this case is going to be I'll put it here, -1.5 plus delta x, which was 1, and this gives us the -0.5. All right, so to get the next sample point, we go ahead and add another delta x here. So add another delta x, and now what's a -0.5 plus 1? Well, that's going to give us a positive 0.5. And there we go. There we have it here. This is our third sample point. Excellent. All right, so now that we know where the sample points are, let's see, okay, well, what is going to be the height for our rectangles? All right, so let's take a look at the first subinterval from -2 to -1. So picking the height here, there we go. We have the function evaluated at, and I'll put it here, at a -1.5, giving us a height. Okay, so let's illustrate it here. Might be a little bit too crowded here, but there we go. So get our first rectangle. Now for the next rectangles, let's see, here's a height for the second sample point. Now remember though, when you're calculating the area underneath the curve, it sometimes might be a little bit of a misnomer, because what's happening now? Well, our curve is underneath the x-axis. So technically speaking, our area is going to be negative. So we're going to get here, oops, So we're going to get a rectangle here that will be giving us a negative area. Now, for the last subinterval, it's going to be the height. And there we go. Now I'm just going to go ahead and label the height here given by the function value, evaluated at a negative 0.5. And the height for the third subinterval was given here by, well, let's put the height given by the function evaluated at 0.5. There we go. Okay, now notice here that it kind of seems that on our first subinterval here, it looks like we might be getting, well, I don't know, it's hard to tell if it's an overestimate or an underestimate, but it's not going to matter too much. Now let me just kind of shade my third subinterval. There we go. All right, so now let's go ahead and get the area. So we're going to get the area by simply adding the total area by simply adding the area for each individual rectangle. All right, so the width here was delta x, which was a1 times the sum of the heights given by the function values. And I'll put the sample points here in a second. There you go, the function value evaluated at a negative 1.5, then the function value evaluated at a negative 0.5, and the function value evaluated here at a 0.5. Alrighty. Alright, so now I want to take the opportunity to show you another way of evaluating functions that I think is better for this type of problems. Because I don't want you to go ahead and plug in a negative 1.5 into the function, then write down the number, and then add up the function evaluated at negative 0.5, put in the calculator there. It can be very time consuming. So what I want you guys to do right now is to go to your calculator. Let me open up mine here. And go to the y equals to menu. So we can type in the function. Now the function was x squared minus 1. Okay. So now that you've created the function, let's go back to the home screen. So second mode to quit. Okay. Now depending on which version of the calculator you have, there are different paths to do this. So the first way that I'm going to explain it is the way that you would do it in the TI-83. Alright, so what I want you to do now is, after creating the function, click on the button bars. And let me increase this so you guys can see my button inputs. Alright, so now that you clicked on bars, what I want you to do is go to the next menu here, yvars. Once you're in yvars, you want to go ahead and select function and pick function 1. Now what are you doing? Well, right now what you're doing is you're telling the calculator to reference the function that you defined here as y1, which in this case was our function x squared minus 1. Okay, now once you've selected the function, the calculator can actually do function evaluations like it does using function notation basically. So I'm going to put y1 of negative 1.5. And what the calculator is doing here is it's going to be evaluating the function at negative 1.5. Sorry, at negative 1.5, which gives us the 1.25. All right, so what you would do next is simply keep on adding the function evaluations here. So I'm just going to go vars, yvars, select function 1, and evaluate it now at a negative 0.5. Perfect. Now I can keep on adding here. Now I'm going to show you the way that you would do it with the TI-84. It's a little bit quicker. So what you can do if you have the TI-84 is simply click on alpha and then click on trace. So once you do that, notice that a menu pops up and it's already listing the yvars. So we just click here y1 and evaluate it at 0.5. Adding everything together here, we get a negative 0.25. So we are getting a negative area. Is that okay? Yeah. Getting negative areas is perfectly valid because we're not getting the area of a geometric shape, for example. No, we're getting the area underneath the curve. It's just that when the curve is below the x-axis, yeah, we get negative values. And we got to see that here in our sketch. There was a lot more area that was underneath the x-axis, so that's why our result was negative. Now, depending on the scenario that the function is trying to model, a negative area can have an interpretation. So let's say that the function here, x squared minus 1, let's say was a model for the rate of change for the revenue, for example. Well, if you found out that the rate of change for the revenue was negative, what that would be telling you, or what the area underneath the curve would be telling you, is that you're not making money. There was no revenue. There was a negative revenue. In other words, yeah, you were kind of losing money. So negative areas are perfectly fine. Again, it depends on the context of the problem. Okay. All right, so now that we practiced a few examples finding the area underneath the curve, I want to take a look at a different type of problem. All right, so we've been estimating the area underneath the curves for given functions, and what I want to do now is practice estimating the area under the curve without the actual function. And example 5 here is, well, a great example of it. So let's take a look at this problem here. So let's say that the odometer in our car is not working, but we still want to estimate the distance that was traveled over a 30-second time interval. Now let's say that we record the velocity every 5 seconds and obtain the following table. So at 1 second, when we first starting our counter, the velocity that we were traveling at was 17 miles per hour. At 5 seconds, we're traveling at 21 miles per hour, 10 seconds, 24, and so forth. Okay, so with this information here, let's see if we can use right endpoints to calculate the distance that was traveled as you went from 0 to 30 seconds. All right, so how do we get the total distance? And what do they mean by using the right endpoints? Because, well, we don't have the function and we do not have the graph. Well, even though we do not have the graph, we do know the inputs, the x values, and we know the y values. So what I would recommend for this type of problems is to essentially create a number line and type in the x values, or in this case, the t values, the time in seconds. So we started here at 0, then at 5, 10, 15, 20, 25, and 30. Now, it's not the best of sketches here. It's not exactly symmetrical, but that's okay. It's going to get the point across. Then 5, 10, 15, 20, 25, and 30. All right, perfect. Now, if you wanted to start creating rectangles here, yeah, we get to see here that, yeah, we could have started creating the rectangles here with our subintervals. Now, since we were looking for the right endpoints, well, you get to see here that essentially we are going to be taking the values 5, 10, 15, 20, 25, and 30. So these are going to be essentially our sample points. Now, another thing that I want to point out right now is, okay, well, what would have been the width for each of these rectangles? Well, you get to see here that the width for each of these rectangles or the subintervals would have been, in fact, let me put it here as delta t, would have been essentially 5 seconds. Alrighty. So, don't forget, the distance is equals to velocity times time, or time times velocity. And I'm going to go write it here as time times velocity, because I want to multiply by the changing time, the delta t. So I'll put here is time times velocity, which is going to be the equivalent here of our delta t times the velocity. Okay. Now, before we can actually get the distance though, there's another important detail to consider. The time was given in seconds, and the velocity was given in miles per hour. So the units are not matching. So for an additional step for this one, we will need to change units. Now, I definitely want to use seconds, but the miles, if I'm using seconds, I'm going to go to meters. So I'm going to go ahead and change miles per hour to meters per second. All right, so if we're going to be changing the units, well, I need to know how many meters are in a mile. And I remember here that 1 mile is the same thing as 1,609 point, and rounding to 2 decimal places, 34 meters. And since I want to use seconds, not hours, I know that 1 hour is the same thing as 3,600 seconds. All right, so I'm going to go ahead and use unit conversions here, and I'm going to switch or change 17 miles per hour to meters per second. All right, so I'm going to go ahead and change the miles to meters, and I know that 1 mile is the same thing as the 1600 or 1609.34 meters. There we go. Now the units of miles are canceling, and I know that 1 hour is the same thing as the 3,600 seconds. So now the units of hours are also canceling, and my units are going to end up being meters per second. All right, now doing the multiplication though, what would we get? Let's see. Let me go to the calculator, and I got, rounding to 1 decimal place here, I get about 7.6 meters per second. Okay, so I'm going to go ahead and use this same operations to convert all my velocities here to meters per second. Now I'm going to go ahead and do this one here, and I'm going to create a new table. All right, so this is the new table that I got where the time was given in seconds, and now the velocity is given here in meters per second. So now that we have the nice same units in time, now we can actually find out what was the total distance traveled. So remember here that the area in a velocity curve, or the area under the velocity curve, is the same thing as the distance. I guess I'll write here, which was the same thing as d delta t times the velocity. All right, so what would we get? Well, let's see, the distance is going to be equals to the delta t, which in this case was 5 seconds, times, now we're going to go ahead and add our velocity values. But because we were picking the right endpoints, we're picking the 9.4 and continue onwards. The 10.7 plus the 13 plus the 14.3 plus the 13.9 plus the 12.5. And let's see, I'm going to go ahead and plug in all of this into my calculator, and let's see what we get. And I ended up getting a 369, but what would be my units? Well, if the time here was given in seconds and the velocity was given in meters per second, well, we get to see here that the units per seconds canceled, which is good. It's a distance, so it has to be in units of length. Now, our units here are going to be meters. Okay, and there we go. So it's a very similar problem to what we were doing. The only thing that could have been a little bit more tricky or easy to miss is the fact that we needed to make sure that we had the same amount of units. So we did some unit conversions, but afterwards we could just read the information for the y values directly from the table. Alrighty, so this is going to conclude our second part of the video. I'll see you guys in part 3. Good luck.